Okay, so let's begin lecture 19, uh, Monte Carlo method, Monte Carlo simulation. The course is NE402, Intermediate Nuclear Engineering, Diffusion and Transport of Radiation and Monte Carlo simulation. This is a full semester course. It will have 45 lectures. This is lecture number 19, where I'm covering Monte Carlo simulation, and this is a continuation of lectures 17 and 18. My name, my telephone number, personal website, official email, and my personal website, www.nucleareng.com. So in the previous lecture, I went through what I meant by an estimator. And so this is an example which let's go through to understand the concepts a little bit better. So let's say that I've got a slab which is finite in the x direction, infinite in the y and z directions, and the two walls are A and B, and I've got neutrons or photons incident from the left face of this wall, and they emerge from the right face of the wall. So, so if I start 6 histories over here, and I label the regions, I define 6 regions inside the slab, then you can see that if with the assumption that energy does not change in scatterings and scattering is only forward scattering. So with these two basic assumptions, let's simulate this. So the first history begins with a statistical weight of 1. Now this blue line shows you a neutron traveling, hitting a host nucleus, which could be anything, graphite, uranium, iron. So when it hits the iron atom or the uranium atom or the graphite atom, carbon atom, so some of it is absorbed and some of them survive. So let's say the survival probability, which is small p, which is sigma s over sigma t, so its weight. So if this is 0.6, so now instead of 1 neutron coming out, 0.6 neutrons have come out. So if these represented 100 neutrons, so now 60 neutrons have come out, 40 have been absorbed. And we'll always keep this number less than 1. So P is the survival probability out of the first collision in the first region. It travels, it does not interact with the second region. It comes out over here in the third region. After the second collision, its weight is P squared. It comes and has its third interaction in region 6, and it comes out with a weight of P cubed. The second history is the red one, which starts with a weight of 1. First collision in region 2, second in region 5, and how much emerges? P squared. So if P is 0.6, then 0.36 comes out. And the third history has its series of collisions in this third, fourth, fifth, and sixth regions, and what comes out is a smaller weight. The fourth history, the fifth history, notice, does not have any collision. It comes straight out. So this is called the uncollided flux. These histories produced a collided flux, and so if you had a detector over here, so this detector would get a straight hit from the source. Now it could be a high energy neutron source, so it could get a straight high energy neutron hitting its detection window. So these are the 6 histories that I've showed you, and here's a little exercise for you, that from figure 510, from this figure, what you're supposed to do is estimate the track length flux and the collision estimate flux. So estimate both of them for this special case, for this very simple idealized case. Are they the same? Also estimate the surface flux, this flux coming out of surface B, if line B represents the surface. So so that's the exercise that you've got to do and apply the estimators from the previous lecture and try to get them. Now let's come to nuclear data processing. A lot of nuclear data is available for elements of the periodic table, beginning from hydrogen, going to U238, plutonium, and and beyond. So the data that was first evaluated experimentally and theoretically, uh, was at national labs in America, and BNL, Brookhaven National Lab, Brookhaven National Labs, BNL, has a lot of contribution over here, and then Oak Ridge National Labs, Los Alamos National Labs, Lawrence Livermore Labs, so Argonne National Lab. So all these labs developed, and then the Japanese evaluations are there, the Chinese evaluations are there. The so you've got uh, a lot of data available in digitized form, and so we call those huge sets evaluated nuclear data files. So ENDF/B, so evaluated nuclear data file B, and I think the current version is version 8. So they contain microscopic cross sections. And these are the cross sections that we use for our simulation to obtain mean free paths and reaction rates in a phase space of interest. So data processing is a big effort in Monte Carlo codes, which take cross sections from these files. Okay, so let me begin a simulation to show you the essential steps. The first thing that you want to do when you begin a history of a particle is to sample from the source distribution, because you have a source of neutrons or a source of photons sitting inside your area of interest, and it's emitting particles. So let's say that you have a source of neutrons which is distributed uniformly in radius. So it's like a sphere, it's a ball source, and you want to sample a particular emission from that source. So where is that? It's at small r, and if the source is of radius big R, then you multiply big R by a uniform random number between 0 and 1, and you can sample the position where you're going to start the source history. So this is the position of the radiation source. Then let's say we need to sample its solid angle of emission. So solid angle of emission has two angles, cosine theta, which is written as mu. So theta is the orthogonal angle, and phi is the azimuthal angle. And I showed you a very good picture in the earlier lectures of omega and its three XYZ components in Cartesian um, geometry. So the cosine theta, written as mu for the ith source which we sample, let's write it as 2 times zeta minus 1. And so if the uniform random number is 0, then this has the value minus 1. And if this has the value 1, because this can only go between 0 and 1, so this has the value 2 minus 1, which is plus 1. So you can see that mu goes between minus 1 and plus 1. So mu is minus 1, meaning cosine theta is minus 1. That is for the case of theta equal to 180 degrees, which means backscattering. And the case mu naught equal to plus 1, when this is 1, it's 2 minus 1 is plus 1. So when mu is plus 1, then cosine theta plus 1 means that theta is equal to 0. So that's the case of forward scattering. So this expression over here covers the entire range from backward scattering to forward scattering. The azimuthal angle, assume that we've got azimuthal symmetry. There's no preferential azimuthal angle. So we sample it between 0 and 360 degrees. So between 0 and 2 pi, we just multiply 2 pi by the uniform random number between 0 and 1. So you'll get the angle phi, the base angle. So with these three things you have sampled a source neutron or a source photon, and you have sampled its initial direction at which it has been emitted. So once the particle is emitted, the next question is, where does it have an interaction? So let me define the probability, this fancy P, that this is the probability that a neutron starting at some position R1 at some time t1, traveling with energy E1 in the direction theta1, phi1, is going to have its next interaction at R2 within dR2 at some later time t plus dt. And so this probability P is going to be the probability of two events. The first is that it travels freely it does not have an interaction between R1 and R2. It travels in a straight line if it's a if it's a neutrally charged particle. It travels in a straight line between R and 2. Now, once it reaches R2, then what is the probability that its next collision lies inside dr2? Dr2 is a very small interval, and dr1 is a very small interval. So you know that when you are interested in a succession of events taking place, then the probabilities are multiplied. For example, if you want to know what is the probability of this and that happening, and the probability of this is 0.9, and the probability of that is 0.9, so the probability of this followed by that would be 0.9 times 0.9, which is 0.81. So if two events have probabilities of 90% each, then the probability of both of them happening one after the other is 81%. Okay, so in the same way, I multiply P1 by P2, and I get the probability of not having an interaction between R1 and R2, and of having an interaction in dr2. So, and I remember when this is the symbol for product. So I is 1 to 2, so this is the symbol of P1 times P2. Now, when I first saw this expression, so I said, how can it be? So what I did was that I didn't write it like this. As a PhD student, I wrote it as 1 minus sigma Tx plus plus plus. I wrote a little infinite series to show that for tiny uh, cases where the probability of not having a collision, and then when you take the infinite series and you end up writing it as like this. So from here you get a PDF. Now, if I'm writing R2 minus R1 as X, so the PDF looks like e to the minus sigma Tx times sigma T dx. And what kind of a PDF is this? As we discussed in one of the previous lectures, this is an exponential PDF. And that is why we had studied this. Because an exponential PDF represents the probability of not having an interaction till a distance x, and then having an interaction at x in dx. Now, I told you that if I ever show you a PDF, the first thing you want is to satisfy yourself that you integrate this between 0 and infinity, because x cannot be a negative number, it's a distance. So the minimum distance can be 0, the maximum distance can be infinity. So if you integrate this PDF over 0 to infinity, you should get 1. And if you do get 1, which you do, then this is a legitimate PDF. And then you can integrate this. It's analytic, so you can integrate this and see that what is the probability of having an interaction till some distance s. So that is the cumulative distribution function, which looks like 1 minus e to the minus sigma t s. So this is a little mistake here. It should be s. Now, if I take this to the left-hand side and this to the right-hand side, and instead of f, if I write the uniform random number between 0 and 1, then this is the expression I get. And again, I've left a minus sign out by mistake, because if this number is between 0 and 1, so the natural log will be a negative number. So s has to be multiplied here by a negative number, which comes from here. So this is how you can sample a distance to collision s. Now, since 1 minus zeta I will go from 0 to 1, so you could also express it simply as the natural log of zeta over here. So we've sampled, so we've had our next collision. We know where we have our next collision. Now comes the question that what type of an event has happened. So for that, we need to see what are the various probabilities. So let me show you a picture which shows you in a little simplified way that imagine an event has now taken place, an interaction at a distance s. So far, we have simulated a neutron or a photon or an electron, and we say now imagine that it can have either an absorption or a scattering. Now, if it has an absorption, then if it has two further possibilities, one that it has a fission, the other that it has a capture. So this is a possible chain of events. So an event could be an absorption, which could be a fission, or an event could be an absorption, which can be a capture, or the event could have been a scattering, and if it had a scattering, then it could be an elastic scattering, or it could be an inelastic scattering. Now, of course, in reality, you've got many of these possibilities, but the important thing is that each one of these chains has a probability. So how do I get the probability of undergoing fission? So if the probability of having an absorption was 0.8 and the probability of having a scattering was 0.2, because these two have to add up to 1. So if an event was 80% absorption, and if out of that 80%, 60% were fissions and 40% were captures, so again, these two have to add up to 1. So if this was 60% and this was 80%, so the probability of following this route and having this outcome was 0.8 times 0.6, which is 0.48. So then the probability of this chain would be 48%. So similarly, you could estimate the probability of any one of these four outcomes. So now we've determined a source particle, the direction in which it left, the distance at which it had its event, and the type of event that it has had. So now we know that it's one of these. So how do we handle one of those four? So what we do is, first of all, if you have a mixture, if you have an element, we proceed now. But if you have a mixture, then in Monte Carlo, you want to know which element inside the mixture does your neutron collide. So if you've got U235 and U238, for example, and you want to know did it collide with U235 or did it collide with U238, so you take this ratio, that sigma t of the ith nuclei divided by the sigma t sum of all the possible nuclides, build a probability distribution function. So you've got a straight line going between 0 and 1, and you can again sample random numbers to pick the probability that comes out of the selection of the random number. Okay, so once a scattering takes place, now we'll consider each one of the above possibilities. So once a scattering takes place, then you know that a neutron is going to change its direction, change its energy. We saw that when we did the conservation of kinetic energy and momentum. Instead of kinetic energy, let me say the conservation of energy and momentum. Okay. So energy could mean kinetic plus friction plus anything. So here let's assume, okay, so this is for elastic scattering. So in elastic scattering, this statement is correct, that it's conservation of kinetic energy. So there's no internal energy change or there's no loss in friction. So the energy of the neutron after the collision is going to be E prime, and E prime is related to the energy before the collision E through this 5.18 in terms of this theta, which is angle of scattering. So this is the picture of a 1 MeV neutron striking a U235 nucleus. I showed you this before for a number of nuclei. I think it was lecture 2 or 3. And in this particular case, you can see that for forward scattering or for backward scattering, the energy of the neutron after the collision is not very different from what it was before the collision. Why? Because remember, a neutron after the collision can have an energy between alpha E and E, where alpha is A minus 1 over A plus 1 whole square. So the maximum energy that can be transferred is in the backward case, in which case the neutron is left with the least energy. So alpha is 234 divided by 236 square, which is very close to 0.983 or something. So 98.3% of its energy is still with the neutron. Of course, in forward scattering, all of its energy almost is with it. So this is how you process scattering. Now let's look at how you process a fission. So in fission, there are two things that you need to do. First of all, estimate how many neutrons are going to come out. So now neutrons coming out could be prompt or delayed. So the average number of prompt neutrons coming out is nu, which is nu naught plus alpha e. This is a relationship as a function of the energy of the neutron. So you can see over here that if the energy lies between 0 and 1 MeV, or the energy lies above 1 MeV, so then u naught is this, and you can get from this alpha is given by this. So you can calculate the number of neutrons for U235, U238 coming out of fission. Now let me show you from a research paper by Schmidt and Jurado. Let me show you some actual experiments that were conducted to determine the neutron multiplication and to actually show that it really is a stochastic process, which means that every time you do an experiment, you do not get the same number of neutrons. So in this experiment for U235, PU239, and CF252. So these are the results of the number of neutrons. Now, can you see the red ones are for the number of photons, and the black ones are for the number of neutrons. So can you see over here that, and these are all, I think, for thermal neutrons. So can you see over here that there's a distribution function? And doesn't it look like a Gaussian distribution function? The normal distribution function that we considered earlier? Well, yes, you can say that it's a Gaussian distribution function. So what we do is we represent the outcome by a Gaussian distribution function like 519. So the mean value is nu bar and the standard deviation is sigma. Now, you saw in one of the previous lectures that rand_n is the MATLAB function that gives you a random number from a standard normal distribution, meaning a normal distribution with a mean of 0 and a variance of 1. So if you want to sample over here, you say rand_n times rand_n times sigma plus nu bar. So nu bar plus sigma times random. Yeah, that's what. And so this is how you get in your simulation, and this is how I wrote a little program. I'm going to show you the results. That this is how I got the number of neutrons coming out of fission. Now, another method to estimate nu from the number of neutrons produced by fission is to just multiply nu bar by the fission probability, sigma f over sigma t, and round it off to the nearest. But I like the normal distribution because it's more realistic. So, well, here also, but what energy would you use? So, okay. So, the energy of fission neutrons, I showed you in an earlier lecture, the Maxwell or Cranberg spectra. So you can sample it from there. So that was a scattering and a fission. Now, how do you process a capture event? Now, capture means that a neutron or photon or radiation has been captured by the nucleus with which it was interacting. So it's gone, and you don't see it again. It's gone away. It either increased the internal energy of the host nuclide, or it resulted in like an N-gamma reaction. N-gamma reaction means that the neutron is gone and a gamma has come out. So we don't want to process a capture as really a capture because it spoils our simulation. So a better way is let's continue its history, but let's reduce its weight so that we get a good answer. And of course, when you carry on like this, then you cannot carry on indefinitely. You have to define a lower cutoff beyond which you'll say that, okay, this is the end, I'm not interested in it. And that cutoff could be 10 to the minus 6, or either it escapes from the system and then you say, okay, that's the end of it. So how do you process an escape from a system event? So when a neutron escapes from the system, it is not added to the updated number of neutrons generated, and thus it does not contribute to the system multiplication. Okay, once you've done this little simulation, you estimate the mean and the variance from what we saw earlier. And remember, this is what the central limit theorem told us, that the variance of your mean, of your sampled mean, is related to the variance of your population divided by the number of events that you had sampled, the number of neutron histories that you had started. So the law of large numbers taught us that you should have an n which is very big to be able to say that it is normally distributed. So if you take a small number of n's, you'll get a very bad result. So if you take a very big number of n, you should get a very good result. Now, what do I mean by a small number and what do I mean by a big number? So Monte Carlo is an art as well as a science. So what's small and what's big are relative terms, and I'll come to you. I'll define a figure of merit, which is a better way of explaining how big or small it should be, how you check. One thing that I showed you earlier was the cross entropy. Remember the Kullback-Leibler divergence? So that's one test of how good your results are. The second test is your figure of merit. But right now, close your eyes and just say that we've got an n big enough so our results are good enough. Okay, so now let's have a pseudocode and let's see that we start an outward batch, an outward loop for the batches of neutrons or radiation simulated, an inward loop of the history of each one of those, and we carry out a random walk for each history. Within the random walk, we've got a number of events. So let's do that. So let's begin with a batch of source neutrons n, and let's simulate g generations for each source neutron. And this is an example of neutrons. So of course, no multiplication for photons or electrons, different story. But let's look at neutrons first. So step one, we begin a source neutron, I. We initialize a counter, n equal to 1. We initialize the neutron generation counter. Nothing has happened. It's just started. So everything goes to 0. So there's no neutron in our bank. We begin our jth uh, uh, simulation, and we begin source neutron k for this generation. We sample the distance to collision, which I wrote above as S, now calling it D as a distance. We sample the type of event. Was it an absorption? Was it a scattering? And if an absorption, then was it a capture? Was it a fission? You process the event like those 4 events mentioned above. You compute the post-collision parameters, which are the E prime and the theta. You determine from your combinatorial geometry, the tests I showed you earlier from ray tracing, that where is this neutron? Is it inside the system? Has it left the system? Which region, which domain of the system is it in? And then you update the counter Ng. You update the number of neutrons that you are simulating. If it's less than the number that should end the simulation, then you go back up to step 5 and you start uh, again this generation. Now, when you do everything for the first generation, then you come here when all the mother neutrons, those neutrons which have produced children for the next generation, when you have produced all the mother neutrons for this generation, then you update your counters for the next generation. See what a huge effort this is going to be. That you store in a bank and you come back and take. So how many do you come back and take? Now that's a very important number. So because you cannot have large fluctuations in the successive number of neutrons that you generate in successive histories. So you've got to keep this fixed. But those are the little tricks that we will learn as we go along. So in the beginning, just say that you're going to look at all of them and get a bad result and say, oh, what happened? Why did I get a bad result? And then we come back and do our refinement. So you score. So remember, this is a process where you learn and learn and learn and get better and better and better. So I first learned Monte Carlo simulation in 1980 when I was an MS student. The late Professor Charlie Maynard used to teach us all this with so much affection, and used to, just like I'm teaching you. So he used to teach us, and he had that thick Los Alamos Volume 1 of the Monte Carlo code, and we went through almost every page of it in one semester. So, so then you've done the first generation, you come back to do the next generation. So you go up in the other loop, you come here when all the generations are processed, you update your source counter, and if you've got more source neutrons, again go up. You see there's so many nested loops. And after you've processed all your neutrons, then you have ended your simulation. And when you've ended your simulation, which typically has taken you 1 or 2 hours of computer time, so you sit and wait and wait and wait and get your result. Now, after your simulation, at the end of your program, you compute the number of neutrons produced in each generation that happened inside, and you computed the K effective for each generation, which means that for this generation, it is the production in this generation divided by the production in the previous generation. And when you've done that, then you compute the error that you have in your estimate, and then you can tell the world that the estimate is K effective plus epsilon. So remember, any estimate you give is going to have some uncertainty. So I'm going to show you when we look at the results that that you should do a track length estimator, you should do a collision estimator, and you should take the average of both of those estimators. So that's the good way of getting a good answer. Now, we did touch upon variance reduction earlier in the previous lecture, and this time I told you I'm going to say what is good and what is bad. So a stochastic estimate is considered to be of good quality. Remember, I told you good quality. Good quality means that if the result is accurate in the sense of the mean, and it is precise in the sense of the variance. So variance reduction is such a big thing in nuclear engineering, in the design of nuclear systems with stochastic codes. Variance reduction is so important that you cannot get any reliable estimate for shielding, for example, if you do not have variance reduction in it. So it is generally understood that if you increase the sample size, good. And how much do you increase? Okay, so let's look at this number, FOM. FOM is a figure of merit. So a figure of merit is 1 over sigma squared t. Capital T is the computational time. Sigma square is the variance. Now, why is it written like this? Well, you can see that sigma square varies as 1 over the number sampled, and T varies as the number sampled. So if you multiply these two, shouldn't they give you a constant? They should. So when you do your simulation, then after each batch, work out the figure of merit and see that are you stabilizing? Are you converging? So that's one test that you can see how your figure of merit is going. Now, variance reduction is a great research topic. So in a course like this, I would think that I should introduce it to you rather than spend 15 weeks with you. So on variance reduction. So this is an intermediate course. So it gives you an overview, it's not just a bird's eye view, a good standard overview with good level of depth to take off for your PhD research. So these 20 lectures are advanced BS and MS. Beyond this 20th lecture, would be, I think, for those interested in research in nuclear systems design and to look at practical applications of applying what we learned in these 20 lectures. So these 20 lectures are the concept, the foundation, the building blocks, and the next 20 lectures are the applications. Okay, so it's a very hands-on engineering type of a course. So perturbations. Now, perturbation theory, the first time you came across perturbation was the Taylor series, when perhaps you looked at y is equal to x squared. So you were told that when x is 2, then y is 4. And what would y be when x is 2.1? So either you can recompute 2.1 square, or you can use Taylor series about a reference point in terms of the first, second, third, higher derivatives and estimate, and that estimate would be called a perturbation estimate. Now, those were for functions that you knew. Now here you're dealing with a situation where you do not have a function. So how can you estimate the effect of a perturbation with Monte Carlo simulation? First of all, can you or can you not? Well, the good news is that you can. And there are a number of ways of doing that, such as correlated sampling or derivative sampling. Now, these are the two techniques which I have applied and understood. So there's correlation. So in the old sense, they used to do a forward run and a backward run, and they used to get the perturbation effect. And they used to do a forward run in deterministic codes using Kino, Timok, Anderson, Dot, those codes, or in Monte Carlo codes. I first started with Morse, the multi-group Oak Ridge stochastic experiment, Morse. It's an Oak Ridge National Labs code. So I started from here because the listing is not very big and you can understand. As a PhD student, I think it's a very good takeoff point. Anderson for those who are interested in deterministic, and Morse for those who are interested in stochastic. So I started with Morse. I did go through all of Anderson, but since my professors, one of his earlier PhD students had done Anderson with the Lagrangian, the forward and backward with Dr. Lewins. Grazza had done his PhD on that, so Jeffrey Lewin suggested to me that why not look at Monte Carlo. So that was a kind of new thing in those days, and so in 1980s I started looking at perturbation with Monte Carlo, and now it's in MCNP. For a number of years it's been there, but it started in those days. So in those days they were called new developments, and so that's when Dr. Reef, the late Dr. Reef, who I was fortunate to meet at a conference in ISPRA at the Joint Research Center near Milan. That's where I met Professor Dubey, Professor Gelbart, who wrote that first book on Monte Carlo, and Dubey, really brilliant mind. So I remember having gone for walks those 5 days with all of them. And these were the people who made this technique, and these are the treasure points in my life of sitting and talking to them. So, of course, in those days, no laptop, no pictures. I had very few pictures there used to be, so I can't show you pictures. But that was, I think, the first conference where I presented my first paper on two-group perturbation theory. And I wasn't sure if I was right or wrong, and there were more than 150 people sitting there, and at least 20 knew what perturbation was, and they were all like professors. So I just wanted a nod from them, and yes, they did agree. So it gave me the signal that yes, I understood, and so then I carried on. So Professor Dr. Reef was using the Kino and Timok codes in Europe. They have a Kino Europe, I think, but I have not used Kino and Timok. So, but then these techniques were extended by Watkins, by Peter Watkins, for material perturbations in in research reactors, and then it was extended by me in my PhD thesis to fusion reactor neutronics optimization. Now I told you I've got a very good paper on this, so you can, that's my first paper and that's my second paper. So the second paper is an application to the Tiber design. Tiber at that time was an American design called the Thermonuclear Ignition Burn Experimental Reactor, Tiber. So what I did was that in Tiber, they were interested in estimating the effect of a blanket and what should be the composition of the blanket and what should be the material distribution. So you can see the paper, my paper of 1992 with Jeffrey Lewins and Asif Kinrod. Asif Kinrod had come from the Sorek National Labs in Israel, and so Asif Kinrod, Jeffrey Lewins, and myself at Cambridge, we did this effort for Tiber. So you can see that there's a paper by Kidrovsky and Brown, Los Alamos National Labs, which compares the adjoint approach with the derivative approach. It's a very good paper, 2011. And I give in this book applications of Monte Carlo perturbation theory in chapter 10, which is going to be the next lecture. So I'll stop over here, leave you with some problems, which every student should do. So take a look at these problems and make sure you understand. The first is on the calculation of pi. The second is to show that you can get a zero variance estimate. Show it yourself. And the third is to write a program to estimate the area under the curve of a normal distribution functions using random numbers you yourself obtain from a normal distribution and compare the efficiency of your computer. So don't take MATLAB as something, which you can depend on. You should know how to generate numbers yourself, because I think that's the best thing, that you should use your own algorithms and you should have your own functions. You should be able to generate your own numbers. Okay, so I stop over here, and I hope you've understood how to carry out a small simulation. So till the next lecture. So I'm going to show you a small program in the next lecture, and then I'm going to show you a big program which does the same thing.